Okay, welcome everybody. I think we'll get going. The numbers are increasing. It's always a period of time like this that the numbers increase in the first 5 minutes or so. But we have a decent number now to start. So welcome to the UK American Ceramics Society and Transforming Foundation Industries Network Plus workshop or mini seminar on sustainable ceramic manufacturing. We all know this is important. We all know this is what we need to be looking at. The title is chosen very carefully to represent different aspects of ceramic manufacturing. You can think of it as the sustainable manufacturing of all kinds of high volume ceramics, or you can consider it to be looking at sustainable materials or materials for sustainability, such as batteries and high energy density capacitors and so on. So it's multifaceted, the title, and it's intended to be so. So we have quite a broad range of topics today, and I'll introduce those at the end as I come to the agenda. First of all, I want to just introduce the team now, which runs the UK ACES. Oops, no, I pressed it. Can you press it? Debbie is doing my slides today. Next slide, please, Debbie. So this motley crew of people, with the exception, of course, of Debbie, the lead people now on the chapter, the UK chapter of the American Ceramics Society. You have myself, who's the chair, the nominal secretary and treasurer, Derek Sinclair and Julian Dean. It's all based at Sheffield. And Debbie has a two-pronged role, and that is she is the marketing officer for the Network Plus, which I will introduce in a second, and helps me coordinate the UK ACES. And I think I'm about to have a big storm, so if you forgive me if it gets very noisy with the rain on the roof. So next slide, please, Debbie. I should introduce also the Network Plus. This is the team that runs the Network Plus. It's all about the foundation industries, so TFI is transforming the foundation industries, in case you think it might have meant something else. And myself as the PI, the co-chair is, the deputy PI is Susan Burnell Lopez from Leeds, Bill Sampson from Manchester, Cameron Plydell Pierce from Swansea. Our industrial chair is Chris McDonald. Debbie, of course, is coincident in both as the marketing officer in one, and the person who helps me organise the UK chapter. And additionally, there's Neil Lowry, who's the network manager. So those are the people. If you want to contact us about the TFI Network Plus, particularly contact Debbie and Neil if you want any further information. If you want to discuss some science, I guess you need to come and talk to me or the others of the management team. Sorry, Debbie, can you progress again? The UK Ceramic Society, or the American UK chapter, I should say, of the American Ceramic Society is about ceramics, clearly. But the TFI Network Plus has a broader remit to focus on multiple sectors, including ceramics, hence we're doing this joint event. And there are themes within the network that are very important themes for the ceramics sector: energy efficiency, resource efficiency, circular economy, next generation processes, informatics, and of course, policy advocacy and equality, diversity, and inclusion, all of which are issues that need to be addressed within the foundation industries and thus within the ceramic sector. Next slide, please. Hello, next one. Is it stuck? Oh, there you go. So if you want to contact us, you can contact me or Debbie concerning the UK chapter of the American Ceramic Society. But if you want to talk to us about the Network Plus, we have a website dedicated to that and an email address here. I won't go on selling you this, but it is a joint event, so I feel obliged to give some information about why it's a joint event and why it's appropriate to be so. Next slide, please, Debbie. So today's agenda, I am pretty pleased with this. You may have remembered that I tried to organize a face-to-face event That didn't happen, and I think I don't need to explain why. We maybe should have put it back into late summer. We tried to go ahead early summer, and we got caught out with the extension of the period for lifting COVID restrictions. So this is a truncated version of that, which is was supposed to originally scheduled to be an all-day event, but we've gone for a short couple of hours to give a flavour of what we would have had in the face-to-face meeting, and I'm quite pleased that the people here have agreed to give a talk. We have Laura from the British Ceramics Confederation, David from Lucidian. We've got some young talent with Jess and Daniel from University of Sheffield to talk about some research we've been going on in my group. Mark has kindly agreed to speak on batteries from Johnson Matthey, and we've got Bill, who you all know very, very well, who's given us a talk on future manufacturing in energy-intensive industries. So a good agenda. I'll introduce each separately as we progress through, but that gives you a flavour, and I hope you realise that it's all about sustainable ceramic manufacturing in one way or another. So I'm going to hand over to Laura, if that's okay, to give us her perspective on challenges in the ceramic sector.
Okay, thank you, Ian, and welcome. Do you want me to share my slides, or?
It's up to you, Laura.
Okay.
If you want to, then please go ahead.
Let's have a go at doing that. Can you see that in the slide for you now? Is that okay? Can you just do thumbs up, Ian, if that's okay?
Yeah.
Yep. Okay, well, welcome, and thank you very much, Ian, for the kind invitation to speak at this event. This is actually the third ACERS event I've spoken at. I'm so pleased to see Bill on the call, because I've spoken at events in 2015 and 17 that he held at Imperial. So I really appreciate the good work that ACERS does connecting those in the industry in ceramics and academia. A little bit about me first. My day job is as Chief Executive of the British Ceramic Confederation, the trade association for ceramic manufacturers. I also, last September, was appointed as a Royal Academy of Engineering visiting professor at Manchester University Department of Materials, and also the Henry Royce Institute, which gives me a great opportunity to work across 7 materials departments in the UK, not only Manchester, but also Sheffield, Imperial, Oxford, Cambridge, Leeds, and Liverpool. And also, as well, I'm co-chair of UK Research and Innovation's Transforming Foundation Industries Advisory Group. So this cuts across the 6 foundation industry sectors, and Network Plus is very much part of this. Very much part of this at the early TRL stage. So I was asked to talk about sustainable ceramics manufacturing. What are the challenges and opportunities? So after a little bit about the UK ceramics industry, I'm going to talk about 3 of the existential challenges that we have, especially net zero, and then go into that. And what does net zero mean? What does TFI mean, Transforming Foundation Industries? And in particular, what does Network Plus mean for our members? And then a message to all of you, whether how can you work with us and support us and our members on the journey forwards. So a little bit about the UK ceramic industry. We've got inputs on the left and customers on the right. As you know, we take clay and other raw materials and energy and equip them and transform them into different things. Now, when the general public think of ceramics, they often think of tableware and giftware, but in the UK industry, that's actually only about 14% of our members' turnover. And I must say, it's lovely to have on the call Paul Scragg from Churchill, who's one of our members. I just noticed him earlier, so welcome. About 55% of our sector's turnover is in bricks, roof tiles, and clay drainage pipes, what we call heavy clay. A further 8% is in sanitary ware, wall and floor tiles. About 8%, only 8% is in technical ceramics. 13% is in refractories, linings for high temperature process, and a little bit that's left over, we've got a number of companies in our membership who are key materials or technology suppliers for the sector. A very wide range of end markets. Obviously, most of the output at the moment goes into housing. So that gives you a little bit of flavour. So a little bit about the energy mix in the sector. And I'm recycling, because that's always a good thing, a slide that our technical director, Andrew McDermott, shared at the Ceramic Innovation Network a couple of years ago. Now, some things have changed on this, I'll explain why. The energy split the sector uses is 86% gas, 2% other fuels, 12% electricity. We are very energy intensive. We have got some electric arc furnaces, induction furnaces, and so on at above 2000 degrees centigrade, but the bulk of the industry's processes are about the range 1000 to 1200 degrees centigrade. We use the gas we use is about 0.5% of the UK's total demand for gas. The electricity, we use quite a lot less electricity than gas. I've crossed out what it cost us a couple of years ago. The electricity price is eye-watering for our sector, £130 a megawatt hour. We don't get the generally we don't get the exemptions and compensations for taxes that some of the other energy intensive sectors do. So companies generally spend more on electricity than on gas. In terms of emissions, about 54 of our 150 member sites are in the emissions trading scheme. Between them, those sites emit about 1 megaton of CO2 per year, which is verified, of course, of direct emissions. Now, the total for the sector is about 1.25. Now, most of those installations are in the heavy clay sector. Therefore, if you want to decarbonise the sector, you have to ensure that there are technologies that decarbonise these ETS installations, especially the heavy clay. We do have some other ones there, like the occasional tiles and refractory site as well. Okay, so what do we make? We're very much a solution provider for the low carbon economy. As you know, ceramics are very durable. They're still Roman ceramics that you see around, and that durability is through the high temperature firing process. So products have very low carbon footprints over their lifetime. And it's not just the energy efficient homes where the high thermal masses from bricks and so on help moderate interior temperatures, keeping houses warm in the winter and cool in the summer, but also durable tableware that can last for years. I think for the thermal insulation, obviously, those of us who work on refractories know without ceramics, we wouldn't have any steel, cement or glass from the refractories. And obviously we make a lot of critical components for renewable energy generation, storage and distribution, whether it's solar panels, ceramics used for the transparent conductive coatings, wind turbine, electric motors, components, or fuels and batteries, which have got all sorts of ceramic membranes, separators, electrolytes, and so on. So, right, I think it's important. One of the things I'd like to highlight on the sustainability piece today is how a more traditional industry like ceramics can adapt to become more sustainable to manufacturing and economic change. So as we went into the pandemic last year, we saw three existential threats for many of our member companies. Firstly, COVID recovery. Secondly, life outside the EU. And then thirdly, the longer term challenge of net zero. Now, while some businesses have recovered strongly from COVID, companies supplying into the car, plane and hospitality sectors still have reduced demand. You know, that doesn't mean the other sectors weren't affected. For example, when the Prime Minister told everyone to stay at home on 23rd of March last year, Most building sites close the next day. Our brick makers and many others, particularly those who operate continuous high temperature processes, had to stop making construction products, but they've recovered well as demand is high for housing. And similarly, technical ceramics and refractory manufacturers supplying into medical or food and drink sectors have done well, but not those supplying into cars, planes, or specialist tough tableware to restaurants and hotels, which won't recover for a little while yet. Now, members have shared with us good practice on working safely. Furloughing helped businesses with reduced demand retain valued employees. And some members found government's free small business leadership program with business schools helped their confidence for more radical changes. Now, some companies had already been increasing technological development, particularly on robotics, automation, automated quality control and process control, and moving sales online by improving digital marketing and analytics, or a virtual interactive showroom. Now, the pandemic has accelerated all this. Now, at BCC, what did we do to support our members? We refocused our work. We had short weekly video conferences with our members and the team at Bays. We have officials who focus on ceramics, which has been great last year. We summarized the relevant, rapidly changing guidance, and members shared questions and shared issues and questions officials. It's actually been a pretty lonely time to run a business. So members say the calls help them feel a sense of connection and solidarity with the wider industry. And of course, with a captive audience, we added in Brexit preparation too, and occasionally bolt-on workshop with experts on tricky issues such as rules of origin and VAT earlier this year. So just some examples to bring it to life. The photo here was when, on the left, was when a number 10 business advisor joined our Bays call. And here we've got Kwasi Kwarteng is meeting with me, the Stoke Central MP, Joe Gideon, and Ros Lynch, a Bays official. Keir Starmer visited a member site last summer. He's visited quite a few over the years. So the pandemic's meant enormous global, economical and societal changes. So I'd like to say something on diversity, because this is something that Ian's network is touching on too. As employers and also at BCC, we've worked flexibly to juggle safety issues and care for children and parents. The pandemic's reinforced inequalities between men and women, ethnic groups, rich and poor. As we rebuild and grow in our increasingly complex and fast-moving world, I know a more diverse workforce gives better solutions and stronger businesses. To do really well in this environment, I think businesses need even more of a diverse workforce with visible role models at all levels to welcome more women, more LGBT employees, and more of an ethnic mix. So that's setting the scene. Now, moving on to net zero. What does the UK ceramic sector need? So we've got 17,500, or we had 17,500 jobs last year before the pandemic, about 1.6 billion of turnover in our membership, and of which just over 600 billion was exported. So the regulatory piece is in these dark and light blue oblongs here. We need a supportive regulatory framework that allows us to remain internationally competitive while avoiding emissions offshoring at all stages of our transition. It serves no good if we just decarbonise by exporting jobs and importing carbon. Secondly, we need internationally competitive energy and carbon prices that don't lead to what's called carbon investment and job leakage, so going elsewhere where the legislation is less stringent. And I've explained about the eye-watering price for electricity. We need something that's much more internationally competitive. Thirdly, we need funding streams that actually work for us as a sector to support industrial decarbonisation, to develop and support a range of technologies and compensate the higher operating costs and support the rollout of infrastructure, which isn't going to happen overnight. We also need policy to focus on consumption emissions. Over the last 20 years, yes, industrial emissions have gone down, but a lot of that has been re-imported from overseas manufactured products. That's no good for the UK or the planet. And we need a greater focus on life cycle emissions to ensure that the policies really do focus on overall decarbonisation. So what does this mean in terms of technology? So what does our sector need? And this is what our members across all those different manufacturing sectors tell us. They need a range of things. I've highlighted energy efficiency, and by that I also mean resource efficiency and formulation changes and so on, because we've got to make what we do more efficiently, and transforming foundation industries very much operates in this space. And I'll talk in a little bit more detail about what that means. But we've got to replace all that gas going through our kilns with something else. Now, what could that something else be? The technologies our members need are various combinations of hydrogen, moving to electric kilns, and bioenergy. And CCUS, carbon capture, use and storage. Why do we need that? Our members who make, particularly those making heavy clay, the carbonates in that clay, and they can only use economically the clay that's locally. When that decomposes on heating to have CO2, they are taxed on that. Now, we are not, it's really important we have some way of dealing with those process emissions, but also if gas remains on the network, then perhaps using an alternative fuel and capturing any carbon generated is another option for the sector. So just moving on, we have achieved quite a lot anyway. We switched from high carbon fuels, the coal, oil and LPG over the 70s and 80s. So they're quite limited other opportunities remain for that because the sites are off the gas grid. Heat recovery from kiln cooling air has been used extensively on continuous kilns for kiln preheat zones, product dries, mold dries, spray dries, warming combustion, air and space heating. So this is a picture from the top of a brickworks, the heat recovery systems over here, top left. Certainly our tile manufacturers and some of our sanitary ware manufacturers have switched from tunnel kilns to fast fire roller half kilns. That fast firing capability reduces the cycle time. So wall tiles now can take perhaps 30 minutes to go through a kiln, whereas previously it took hours. We also have, this is lightweight insulation, low thermal mass refractories, and also obviously on kilns maintenance improves heat losses. Burner improvements too, and setting them up correctly, and new burner technology, pulse burners and high velocity burners in excess of 100 meters a second have all been used. And obviously members work on process control optimization, improved temperature and airflow control. Reformulation of body and glaze recipes can help drop firing temperatures by 20, 50, 100 degrees centigrade, or they can indeed eliminate firing steps. So for example, this, this tile factory moved from a batch process using twice fired to once fired. And conventional energy efficiency measures are common across all factories, quite often used here: motors, variable speed drives, lighting, energy efficient lighting, compressed air, and so on. So this next slide on transforming foundation industries, and I'm just speaking very much as co-chair of that group here, as we're focused really on 3 different types of technologies that cut across the 6 sectors I've listed at the bottom of the slide. Firstly, heat recoveries. Secondly, sensors controlled digitalization. And thirdly, waste utilization and symbiosis. So using waste products from one industry or sector to reuse elsewhere. Now, some sectors will want to focus on 1 or 2 of these challenged areas. And I'm going to talk about what we think, what our members say is important in this area for us. And what's important is that more than one foundation industry needs to benefit from the projects. But for the Network Plus, there's slightly less of that strong link. As long as it's got some, I think, some possibilities for use in other sectors, that would be great. And Network Plus, this very early TRL. Now, when I'm chairing the group, I do try and put my, I try and look across all 6 sectors, but also as a taxpayer, it's really important that the largest sectoral energy and resource efficiency challenges do need addressing, not just the peripheral or esoteric projects. So one of the reasons for doing the presentation today is to just try and inject that dose of reality, and if we can get some focus on some of these ideas, that would be fantastic. And I have had some great conversations with Ian over the last few months as well. So I'm just going to try and bring those to life a little bit. For us, the heat recovery is about durable low-cost heat exchangers for kiln exhaust. This is something our energy and emissions group and our low carbon working group at BCC keep on talking about. So it's about corrosion resistance to acidic kiln exhaust gases. If you remember, I said we can recover heat cooling down, but as you're heating it up, you've still got some moisture in that. And that's obviously more expensive to heat recover from. But if we can do it, that's great. So it's got to be cost effective. So one of the technologies our members are quite keen to look at are demonstrating heat pipe heat exchangers. And we're always keen to learn from other foundation industry sectors too. On the sensors, control and digitalization side, that's one of these sort of heat pipe heat exchangers. It's how can you get those improvements in real time measurements? Some of our member factories, whether it's a brickworks or a loo factory or a tiles factory, they do have quite good computer control systems on them, and they are monitoring the sorts of defects that they have. So part of the challenge could be, how do you gather that data, perhaps using AI, perhaps in real time, to learn from what's going on and help improve that process control a little bit more, rather than just looking at the data as a team at the end of the shift and thinking, right, might need to tweak that a little bit. So those are a couple of the ideas on those three themes from our sector. So let's go back to net zero. There's an awful lot that hasn't been covered as well. What about replacing all that gas in the kiln here and the CCUS? So just moving on, I'm just going back. On hydrogen and CCUS, governments designated some special industrial cluster sites. These are the grey ones that I'm just pointing to around the UK. And our ceramic manufacturing sites are generally nowhere near them. So it's actually, and many of our member companies are in the our SMEs. So we've got a small cluster in Staffordshire. So it's actually really challenging for us to be able to access government funding to CCUS and hydrogen. Now, that has not stopped some of our members trying, but they haven't got anywhere with it. And that does need to change, and quite rapidly. We do need that portfolio of viable ceramic decarbonisation technologies. Just a little bit about all of those 4 technologies. There's a lot of noise around hydrogen as a fuel. We are off cluster, and our low carbon working group at BCC has agreed a programme of work to explore that, but there's no government co-funding at the moment. And I know that hydrogen burners are being developed around the world. I think a key thing for us to focus on, I know the material scientists on the call will really appreciate this, what is the impact of hydrogen on the product, its properties, the refractories, and also the pipework. I'm speaking as someone who's doing my PhD on hydrogen embrittlement and duplex stainless steel, so I really feel the pain here as well. There are other issues as well around hydrogen. On electrification of heat, this is just a very small continuous electric kiln. I mean, I saw one a few weeks ago. It's about 15 meters long at a member site. They do exist, and there is a need to develop much bigger versions. The alternatives to the gas-fired tunnel kilns and the fast-fire roller kilns. But there are undoubtedly some technical challenges, but the primary challenge is clearly economic, given that first, we need internationally competitive electricity. And secondly, you can't, whereas with hydrogen, at least you've got a chance of replacing natural gas with hydrogen and perhaps doing a few changes on the burner materials. But you really would have to scrap a gas-fired kiln and replace it with electricity, but that may be the only route available to some of our members. On the biomass and syngas, the fuel switching isn't proven for some continuous 24/7 at scale operations, or it wasn't a couple of years ago. And there are issues around tar buildup problems, and those need to be tackled cost effectively. Now, our low carbon working group has done an outing to, they took a group of members to look at a pilot bio gas project being developed in Swindon to gasify curbside recycling, just to see what's involved, because if members are going to need something like this on site, they need to understand what the technology is. And on CCUS, this is one of our members was successful in getting some feasibility funding, working with a technology provider and a downstream user to use all the magnesium carbonate generated, but it narrowly missed out on being taken to pilot plant stage. I was really gutted at this, and it is now almost certain to be taken overseas as a technology, which I find really, really sad. So my last slide, how can you work with us and support us and our members on this journey? As you've seen, a lot of the government funding streams won't actually at the moment support the development of these technologies. We are putting in a spending review proposal on a portfolio of viable decarbonisation technologies for the whole UK ceramics manufacturing sector. Now, this is something that our management committee, that's the equivalent of our board, absolutely endorsed. We have to work on this collectively. This is too big just for one company to tackle. In parallel with that, once technologies are proven, we started in the last year our Towards Net Zero initiative to share good practice with members on implementation. So my closing words here, if you want to work on any of these projects, and whether it's a Network Plus type project or another type of technology, and you're a UK ceramics manufacturer, a technology provider, a materials provider, or an academic, please do get in touch. So I put my email here, and also my colleague John Flitney. So I hope that makes sense to you. I've left some time for questions, so look forward to hearing what you have to ask me.
Thank you very much, Laura. That was a fantastic overview of what we need to do to make things move towards net zero in particular. It's a big challenge, and you set out the challenges quite beautifully there. I just like to make one comment. You mentioned the Network Plus, and well, I didn't expand on it in my introduction, but we do have a sequence of small project calls. We've just completed one, and we'll be announcing the results of that soon on energy efficient manufacturing. We've just got the okay to move ahead with one we're announcing in the 23rd of July, I think we're going to announce the call, and that will be industrial symbiosis, circular economy, resource efficiency in that area. So that's the next call. So if you're interested in doing that within the ceramic sector, or any sector, but particularly here, the ceramic sector, please contact the TFI Network Plus team, and we can guide you on how to do the submission. The upper limit is about 60k, so it's around six months of funding, and it must be led by an academic, but that means, you know, it can be co-created by industry, but led by an academic, since it's EPSRC based funding.
Are there any more questions? Are there any more questions if we've got a couple of minutes?
So you have a question in the chat there, Laura. Any initiatives in terms of non-fired ceramics?
Any initiatives? Those are not using lots of energy. So although we have a handful of members in our membership who make non-fired refractories, our focus has absolutely got to be on those really big emitters. that doesn't mean to say that you shouldn't be doing a lot of the energy efficient things that cut across other sectors. So, for example, I know that some of our non-fired refractory members have put in things like variable speed drives on mixer motors and things like that. So there's a lot of technology that can be transferred from other sectors, but the bespoke stuff for ceramics does need to focus on the big emissions in the sector.
And don't forget that TAVs, isn't it? That grinding is a big energy user in the ceramics industry. Even if you get raw materials at your factory door, at some point they've been ground into raw materials where the mining is and the extraction is occurring. So I think there are initiatives to look at grinding reduction, energy reduction in grinding, and lessons to be learned from the mining and extraction industry if you do any on-site milling, grinding, and so on of your raw materials. So I think we had a talk on that in that energy efficient workshop a couple of weeks ago from someone from the mining industry based in Singapore, and it was very interesting what was being said there and the strategies you can use.
That's good to know. I think because almost every ceramics manufacturer does use solids processing, and that is a big user of electricity, and I'm looking at Paul Bingham's question as well. The biggest challenges to develop the enabling technologies you need are the engineering ones or the material ones? I think it is generally the engineering ones. I know it's really dangerous saying this to an audience of materials scientists, but clearly there are some important materials challenges, like for hydrogen. We have to ensure that firing in hydrogen doesn't embrittle the materials that we're making, doesn't damage the mechanical, electrical, and so on properties. And there's another question: any appetite for low sintered ceramic? I know there are presentations on, for example, flash sintering and later. This has not come up as a technology that our members need as a technology for decarbonising. Particularly, again, focus on the heavy clay sector. What is practical, and it's about using the clay next door to their factory. But I'm always keen to listen and learn from others as well. We have to develop technologies that decarbonise our most intensive producers. Have I answered all the questions there? Has synthetic biology for manufacturing new materials been considered? Oh goodness. If T, I guess I'm not sure about where that might be for some of the technical ceramics. I know perhaps some of the carbon capture and use technologies might, people have been looking at biological solutions for that, but for end of pipe solutions. But we have to think about the economic as well as the technical practicability. I think that's captured all the questions. If I've missed any, Ian, could you let me know?
I don't think so. I think you got them all, Laura. Very well done. Okay.
And are people happy with how I've answered them, or is there anything else you want to check? Okay, well, if you've got my email, just drop me an email if you want to follow anything up, and look forward to hearing from you.
So thank you, Laura. That's fantastic. Some really deep questions there. So a very useful and important contribution. The next speaker is going to be Dr. David Perman from Lucidian, who's the head of flash sintering. Laura mentioned flash sintering. Perhaps it's got its main uses in more technical ceramics, but I'm sure we'll learn more from David's talk, which will be on next generation sintering, the scale up and benefits of flash. David?
All right.
Hello, there you are.
Yeah, thanks very much, Ian. Sorry, a bit of a delay there.
Or is Debbie going to do this for you?
No, I'm just sharing now. Here we go.
Thank you.
Everybody see that all right? Is that all good, Ian? Okay, all good. All right, well, thank you very much for the invite and for listening to me today. So yeah, I'm going to talk a little bit about the next technology in terms of sintering and the application of electric fields to ceramics during a sintering process, and give some ideas on how that's really contributing to increasing productivity and energy reduction in the ceramics industry, as well as enabling next generation of products and so on. So I'll fire through this. All right, there we go. Okay, so what are we doing at Lucidian? Well, we're looking at flash sintering itself, and that can be in some applications via sandwiching a ceramic between two electrodes and applying an electric field during the sintering process. And I'll go into a bit more detail about what that is, just in case some folks don't know. Then looking at contactless flash sintering development, that has various applications, talk through them. Something we're doing on a Transforming Foundation Industries Innovate UK bid, working closely with Ian and the University of Sheffield at the moment, is looking at the cold flash hybrid sintering system, and then looking at how we can join materials and some applications of that. So covering quite a lot, but hopefully a wide range of industries and technologies covered to give you a bit of a flavour, and then how we're going about scaling these up and where we are in terms of TRLs. Just a bit of a background first then. So if we think of flash sintering as you contact or apply an electric field to a ceramic at a furnace temperature. So that would typically be, say, let's take zirconia as a technical ceramic example. If we apply an electric field at 800 degrees and then apply a voltage across the ceramic, you're getting an increase in conductivity, and then you kind of arrest that power spike and run away and have a consistent current through it. And that kind of provides a real rapid densification. So what you're getting is sintering in a matter of seconds, as opposed to a number of hours, and that's generally occurring at furnace temperatures of, say, 700 to 1000 degrees instead of, in the case of zirconia, 1500 degrees. So this is one of the, I must say, a good example of this is kind of a video of the discovery of the flash event, let's say. So it's kind of called flash because, well, perhaps because it happens as quick as a flash in the case of the discovery of the thing, but often it optically emits as well. So if I just play this for you, you see this kind of rapid shrinkage and the optical emission there, and that's it sintering in very, very rapidly. So we tend to find that this sort of the simplification of this technology is quite prone to localization, and you've got in the case of this rod that you're seeing being sintered here, you've got kind of an over-sintered middle and an under-sintered outside where the thermal losses haven't done that. So at Lucidian, in order to make it scalable, we kind of don't just think of it as a process that takes seconds, but almost sort of seconds to minutes. And we've built software and electronic control systems to ensure that it's scalable and homogeneous sintering on pieces, real ceramic pieces. Okay, so yeah, why would we bother getting into kind of electric field sintering? Well, actually, I guess productivity is one of the main things. So we'll talk a little bit about fuel cells and using solid oxide fuel cells, and it's a very slow manufacturing process, often on supported metals with multiple layers of ceramics, and kind of a pain to sinter and a drawn out process. Actually, our contactless is developing a system whereby if we can increase or double or triple the productivity and the number of parts you can make per day, you can reduce that cost base and therefore have a green technology become available for a wider variety, not just specialist applications. So productivity is a real significant kind of impact, especially with its link to the green technologies such as batteries and fuel cells there. And then also, of course, energy reduction in terms of its Laura spoke about the high temperatures that these furnaces use, a lot of carbon being burnt, so a reduction in energy consumption and furnace temperature. And then also, can it enable new products such as microstructural control and bonds between ceramics and metals? So I mentioned quickly, I won't spend long on this, but we've got a development software piece that we've seen, and this really monitors. It's a non-linear real-time control software. So it kind of reacts with our application of the field to the ceramic and can adjust in milliseconds so that we don't have any of these kind of defect hotspots formed by the process, and we can operate over larger surface areas. We're very customizable. You know, it's a materials dependent process, so it needs to be optimized for each of these materials and geometries and scales. We do DC all the way through to high frequency AC, and there's some interesting effects there. I'll give some examples in this of you know, how the control system enables scale up where we're working in nuclear fuels, multi-phase materials, ceramic to metal joining. There is some interesting effects on the more traditional ceramics, such as tileware. Then looking at things like armor, aerospace, and some of our work in the refractories so far, and with the cold flash hybrid, and that's directly off the back of Ian's great work with our project on in the TFI stuff we're doing on glass, electrolytes, and refractories. Okay, so just come back to sort of the fundamental zirconia example. I'll show you this is a cylinder of zirconia sandwiched between two electrodes. You're seeing a non-linear shrinkage there. That's kind of some optimized flash settings, but without the use of the controller. Then if we go into where we switch the controller on and it's doing its thing, we start to then see a much more uniform shrinkage across a bulk piece of ceramic. But then as we start to optimize and really look at different flash settings, what we can start to see is conventional sintered microstructure here, and this is uniform. All of these images represent a cylinder of zirconia that is the same density that's achieved in conventional. We've got five hours at 1500 degrees here on the right hand side on the micrograph. But then if we start saying, we'll call it flash sintering, I suppose one could argue it's not flash sintering if you take 83 minutes, but in terms of the application of an electric field using our controller for 83 minutes at a furnace temperature of 1050, we get a comparable microstructure to that that's conventional again, and that's consistent across the breadth of the sample there. Then as we go down to 9 minutes or even into that seconds regime, 80 seconds, we start to see that this density can be achieved, but you can retain a much smaller grain size for fully dense samples. Now this has then applications in the performance of the material, and indeed for silicon carbide and stuff that affects the hardness. It's been quantified as well that we can increase the strength of these zirconia bars by 10 to 14% in terms of the strength of zirconia bars by 10 to 14% in comparison to conventional sintered techniques. So yeah, very interesting, and that has some applications in terms of dentistry, orthodontics, and things like that. When we look at kind of these, if we think of more ceramics as more traditional ceramics, maybe that is an inert body surrounded by liquid phase or vitreous phases. In our case, this formulation is kind of a waste container glass, so recycled glass. We have to have a very different approach because we're using liquid phases that love to localize. So we actually pulse the sample with energy here. And this is a 5 by 5 centimeter tile that's 11 mils thick, sandwiched between two electrodes again. So it happened really quickly. Oh, sorry, 8 mil thick there. Sorry. There we go. Just kind of happens very rapidly. But as we start to play with the frequencies that happen that we can use as one of the electric field variables, we start to actually be able to get more energy into the sample without it localizing. And we can start to not only encapsulate all of those inert particles by igniting that liquid phase, but we can actually start to interact and start to melt those inert particles as well. And we get a different microstructure, which is very interesting. But in comparison between high frequency and low frequency, which would have some effects in terms of the performance of the material, but not necessarily relevant to a traditional sort of tileware body, as we sort of talking about here. Just a little quick in video of a smaller sample here, much smaller sample, but where you don't have an optimized settings or use of the controller. You'll see the sample kind of raise up. And then just at the end, you see that kind of gloop that it's now sitting on. That's actually, as you ignite that liquid phase, it's just oozing out the bottom, where you've got kind of that non-controlled sintering using the electric field. So bit more high tech, but nevertheless contributing to carbon net zero in terms of the use of nuclear energy. We're a member of the Advanced Fuel Consortium, and we have a partnership with University of Manchester and National Nuclear Laboratories. We did some work, of course, this is on surrogate fuel materials to prove the concept here at Lucidian. But actually now we're working alongside both of the collaboration partners, and we're now sintering uranium dioxide and moving to mixed oxide trials. And that's recycling of nuclear waste, but also looking at the next generation of modular fuel reactors, fuel for fuel reactors. So the picture you're seeing is kind of the development of the nuclear fuel pellets for the surrogate cerium oxide material we did. Typical over kind of a 5-month process, you go from blowing holes in the sample where you can see the melted middles, and then you start to find the field parameters that work, and then you actually start to get homogeneous sintering or in field interaction that's not localizing, but you're still not sintering the whole pellet, all the way through to the far right now, where we're reliably churning out these fuel pellets on surrogate fuels without any cracking, without any stress induced there, and hopefully homogeneous. And again, that was done at a 35% reduction in firing temperature and a 50 to 80% reduction in time of sintering. So some real sort of benefits of application. We also showed that microstructural control was possible. Now, I spoke about the fact that retaining small grain sizes to increase hardness or strength in some of these technical ceramics or advanced ceramics is important. For nuclear application, they want big grains, so you don't get any of these off gases trapped at grain boundaries, and this can increase the lifetime of the fuel. Longer lifetime means less plant shutdowns, which can cost 2-3 millions at a time, and less waste produced. So some real potential benefits. So we're working on the recycling for fuel for future reactors and the future fuels program with NNL, and looking down the line to install some of our kit that's developed with them at the MOX mini fuel line, and then hopefully into manufacture for the nuclear sector. So some quite exciting developments there in the last year or so. We've been working hard during the lockdown on this stuff. So that's kind of summarizing some of our contacts work. I'll breeze through so I catch up on time. But if we think about where we can't use it in a contact area, but we want to ignite a plasma and raster over the surface. So we looked at repairing glazes, where you might drill out a defect, fill it with glaze, and actually lower a furnace, an electric field across to melt that and manage the thermal differential. Now, this would reduce the need for an entire refire kiln potentially, so significant carbon savings there. What we've done though, I'll skip through, is we've actually now gone from kind of looking at repairing these glazes to actually sintering solid state electrolytes on metal and on various substrates. So we've got a robotic arm that's synchronized with the nonlinear controller, whereby we insert an electrode into a low temperature furnace, and we can control really quite accurately that. Forgive me, I'm skipping through some slides here just so I don't overrun and frustrate everyone. But here it is in action. So this is I guess the main interesting bit. Here you're seeing a metal base with a solid state electrolyte layer printed on top, and this is a very simple electrode setup, but we're rastering an electrode over the top. And this is precisely to increase the productivity and the amount of time it takes to sinter these multi-layered materials, or indeed these solid state electrolytes. So you can clearly see sintered layers next to green, still green layers there that we're looking at. And indeed, this is just a picture of what you're seeing, where we're rastering in a different direction. Now, there are many different factors it took us to get here, and there are various different electrode setups. And indeed, now we're using this technology to seal the surface of ceramics to produce graded structures as well, which is all quite exciting. And we've got a new Innovate UK program where we're looking at using this technology alongside additive manufacture for battery applications. Right, there's a phone going off in my room, not sure where that is. But when we look at scale up, then we're also in parallel to that kind of prototype technology that I just showed you. We're looking at developing that. And so we're working with an specialist equipment manufacturer. And here you can see sort of the production of fuel cells, kind of we're sintering half A4 pieces here, where we're looking at multiple electrode heads rastering to produce X thousand of pieces per day. And that's been quite effective, and these guys have shown what's possible in terms of the many different setups that are possible. So we're already looking towards that kind of pilot line scale system for contactless work, and then furnace design is underway in terms of preheat, pusher, pick up and place systems, various control systems, so industrializing our nonlinear real-time controller, and then looking at use of vision systems for that as well. So some images to represent what we're doing there, and then some of our work that we've done. So kind of hopefully gives you an idea of exciting kind of where we are with Flash, and how we're actually moving through those TRL levels to make this a reality and kind of enable the next sintering technologies in industry. Also then I mentioned we're sintering ceramics on metals, but then what does that mean for the bonding and what's possible there? I can't go into detail here, but looking at bonding ceramics. And then finally, Ian's and our work on the application of both. You may be familiar with cold sintering and the application of a electric field with that process. Some of the emerging work that we've got coming out is actually looking at refractories and refractory ceramics. This is our prototype here that we've developed, whereby we're applying the pressure through the cold sintering as well as the electric field through the sample. And actually some of the work, we've taken the Ian and the Lynn Howe's cold sintering settings, and we're reducing the furnace temperature all the way down to room temperature up to 60 degrees, and we're actually achieving some quite nice 60 to 80% dense alumina-based, alumina silica composite ceramic materials for one of the industrial partners. So quite an effective. The initial results show this process to be quite effective, but it's very early work, and watch this space. Could be relevant for many different applications as well. But of course, being limited by potentially that pressure, how big can we go? And that's the next task for us to scale up. Excellent. So I think I've tried to finish on time there. Hopefully summarize some of our the potential for the use of electric fields in the next generation of sintering technologies in terms of toughening ceramics, increasing productivity and reducing energy consumption. There are still challenges to be overcome, but hopefully given you an idea of how we're overcoming those already in terms of our scale up in certain industries for the next, and hopefully cementing the future of British ceramic manufacturing, keeping us competitive in terms of technology and energy consumption, or playing a small part in that at least. So thank you very much for listening, and happily take any questions, and feel free to email me or reach out after this if not. Thank you.
So thank you very much, David. That was a fantastic talk. I think there's some questions in the chat.
Yeah, perfect. I'll just stop my share
So
there.
there's one from Daniel. I can't get it lined up. Does the rastering process of contactless sintering produce any boundary effects between each rastered line?
Yeah, so obviously that's an important factor to avoid on when we're sintering whole sheets of, you know, of the kind of, if you think of the fuel cell sizes. So in many occasions, no. I guess that at some point it would. I guess it depends on the thickness of your ceramic that you're trying to sinter. There could be mechanical effects be introduced, and so on. So for the applications we are working on, we've either got rid of them, overcome them, or the answer is no. But yes, there would be at some point, depending on that application and geometry of what you're looking at. So it's very dependent on the application and the material.
Do we have any further questions for David? I think in the interests of time, we'll probably move on. I will ask you to email David about any further issues, any interest in the flash sintering technology. It is an exciting technology and it can do quite miraculous things. I think some of the stuff that we're doing is quite brilliant over at Lucidian. So thank you, David.
All right, thanks very much, Ian. Thanks, everyone.
So now we're going to move on to some University of Sheffield-based researchers. This is our youth policy. So Jess is a newly qualified PhD student, a postdoc in my group, and Daniel Button. That was Jess Andrews before. Daniel Button is a senior PhD student, not a PhD postdoctoral research associate as it's got here, but a senior PhD student. And they're going to give a talk based on the research. It's going to be a double talk, and it's going to be based on cold sintering of advanced ceramics and glasses. Cold sintering was briefly mentioned by David, so this is a kind of follow-on, and to give you a feel of what can be achieved by this technology.
Thanks, Ian. I'll just quickly share my screen. Can everyone see the slides?
Yeah, that's good, Jess.
Yeah, okay. So as Ian said, today we're going to talk about some of mine and Dan's work on cold sintering of advanced ceramics and glasses. So firstly, why would we look at reducing the sintering temperature of ceramics? Well, as Laura said earlier, something like 35% of costs in the ceramic industry are related to energy. And the table on the left of our slide just shows how much of a reduction you can get for sintering 1 gram of barium titanate by cold sintering versus solid state. And that's about a 99% reduction. So that's a huge impact that can be made quite simply. Another major benefit that we've got is if we reduce our processing temperatures, then we can improve the sort of different materials that you can add into your components. So you can co-sinter with a broader range of metals with lower melting temperatures and lower glassization temperatures, but also at sort of the 200 degrees and below, you're looking at getting lots of polymers involved, and so you can make some really exciting structures. Cold sintering is a fairly it seems a fairly simple process. There's lots of science that goes behind it, but eventually you end up mixing a transient solvent with your powder, and that encourages dissolution into that solvent. You then apply a uniaxial pressure and heat your whole system, and that allows the liquid to evaporate again and hopefully leaves you with a nice dense ceramic that's got some useful properties. So sometimes you need to do some heat treatment afterwards to retain the properties that you want. But there's some really interesting science being done to get dense, like sort of super dense bodies once you've just done something at sort of 200 degrees. So Dan's going to do some talk to you about some of the work he's done on zinc oxide.
Hello, can people hear me okay?
Yep.
Cool. Yeah, so I've been working on zinc oxide. Some of you may be familiar with it. It's a very, very common material found out. For material scientists, it's a hexagonal wurtzite structure. It's generally used in things like varistas that you see in the top left, or some applications that it's posited to be used by is in transparent conducting oxides, which is the thin layer that goes on top of solar cells and is responsible for the conduction through the solar cell, and it's very, very important. And we want to replace things like indium tin oxide, which indium is quite toxic and it's quite difficult to source and very, very expensive. So if you go to the next slide, please. So this is some of the work that I've been working on. Zinc oxide has been cold sintered. There's quite a lot of literature through it, but we're now getting sort of down into the science of how that we're cold sintering it. And the effects of things like powder size. So the top row you can see is a very, very small 10 to 30 nanometer powder that we used. And the bottom is a far more general out of the pot Sigma Aldrich less than 5 micron powder that had a very wide grain size and the effects of cold sintering. And as you can see, both with the 300 degree and 375 megapascals achieved a very, very dense structure that would be typical of a conventionally sintered structure, even though it has a very small grain size. And you can also see in the center, with just a slightly lower pressure and temperature, there is a very large difference in the shape of the grains. So the smaller grains, which showed more grain growth, gave a more columnar structure, which will of course affect the properties, and the larger powder gave a more varied grain size because of the starting powder, less grain growth, but did still densify, but maintained a more spherical grain structure. And so these are the sort of the things that we need to look at to if you want to start scaling up and controlling this process. So next slide, please. So on the left there, you can see a conventionally sintered zinc oxide material. It's usually sintered at 11 to 1500. Extremely large grains produced, except the pores are still very large, so you'd still need a bit more energy to get much higher densities. And the cold sintered material on the right, much smaller grain size, but has had the benefit of that compression during the hot pressing, and so achieves consistently above 99% dense, near theoretical density. But again, you've got this columnar structure coming through, and this sort of things we need to look at. Okay. So there's been some things in literature, because we mix it, I should have mentioned, not just with water, but we use acetic acid, so basically vinegar, the vinegar that we use, and understanding the fact that sometimes you can observe a residual acetate phase. Now, the work that we've done, that I've been working on, I did notice that after the cold sintering, I did need to do a bit of a heat treatment to remove that acetate phase. Other groups have shown that it actually removes itself at 300 degrees. So this comes into the factor of understanding controlling conditions, and perhaps different equipment setups are very, very important to understanding this process and optimizing the best we can. So other work I did, to create the transparent conducting oxides that I mentioned, you need to increase the conductivity if you want to get anything close to indium tin oxide. Usually this is done with the introduction of gallium or aluminium, sometimes both. We did 2% gallium, some powder was produced for us, and we wanted to see if we could cold sinter it. The answer is yes. It did need a slightly higher temperature than the normal cold sinter stuff. You can see on the far left, basically there was almost no densification that took place at 125 centigrade, which would show a bit of densification with cold sintering usually. This is expected, however, as the introduction of the gallium oxide, which incorporates itself into the grain structure, is well known to inhibit grain growth and densification, even in conventional processes. Just a factor of note on the far right, this is a top surface view. When we increased the pressure significantly, we suddenly got a constriction effect, which caused enormous grain growth in the XY direction, which sort of counteracted the usual slight increase in Z direction growth you get with cold sintering sometimes observed. Yep, oh, next slide, please. The GZO showed pretty much, so the top is conventional and the bottom two are cold sintered at different conditions. You can see in the top left. Next slide, please. They're very similar to zinc oxide. However, the conventional show the presence of a zinc gallate, which is a well-known spinel structure that tends to form. There's the debate on whether it's actually useful in the material. It's got a very different band gap to and conductivity to zinc oxide. Now, our general consensus is no, it's not generally good to have a random secondary phase appearing in your material, but regardless, it didn't seem to form in the cold sintered material. However, we did double check with some high resolution XRD. Next slide, please. JM very nicely did for me. And it did show that in the cold sintered, there was a very, very small amount of this gallate phase. Now, it is still present, but it means that with the cold sintering process, we can perhaps control it if it's control it much better if we do want it, and it does reduce significantly if we don't want it. But yeah, these are significant pressures. Usually you'd have to go to something like 12 to 1300 to actually get rid of this gallate phase. So it's a significant reduction in temperature. Next slide, please. And finally, the transparent part of the transparent conducting oxide. We wanted to see if we could actually layer this material onto a polymer. So Kapton is the orange plastic that you can see, it's why it's orange. And we used a tape carting process that I can't go into the details of. And we used a cold sintering method to densify zinc oxide directly to the surface of this polymer material and created multi-layer structures, and it maintains transparency. I will note, that will surprise you all of you, the 2 on the top left is actually underneath the device that we produced. The grain structure showed to be very, very similar to conditions that we sintered it at for bulk material. So yeah, it's really, really fascinating what that's gone on. I'll now move on to Jess, who's going to describe the work she's been doing.
Thanks, Dan. So I took a bit of a sidestep. I started with functional ceramics and then moved into using the cold sintering process for glass-based materials. And one of the really exciting things we looked at was bioglass, which is a 4-component glass with silica, calcium, soda, and phosphate. And it's really highly bioactive, and it encourages the bonding of implants in the body. There are issues though. It crystallizes readily at 600 degrees and during slow cooling, which means that most of our conventional sort of processing and coating correct temperatures would potentially increase crystallization. And that crystallization has been shown to hinder the bioactivity, so it would reduce how well implants and things like that bond in the body. So I used distilled water as the solvent at a much higher volume than we would normally see in cold sintering, 88%, and then pressed it between 50 and 250 megapascals for 60 minutes at just 100 degrees. And you can see on the SEM images that we've got there, the top surface and sort of the cut through fracture surface. And it's really quite dense, and there's lots of there's sort of some areas in the fracture surface that look a little bit denser, but that's from the original powder. So that's kind of telling us two things: that we're retaining structures that are in the original powder, which could be a positive if you want sort of specific structures, but also that we can make a really dense bioglass piece at 100 degrees really quite quickly. There are sort of, when you implant bioglass into the body, there's a number of sort of processes that it goes through, and the first 5 are really important to understanding the mechanism behind why bioglass cold sinters and how it cold sinters. So you get some alkali ion exchange, network dissolution, and repolymerization, and then you also get the sort of the beginnings of a crystallization of a hydroxyapatite layer. So we did some NMR with the help of Warwick University to look at how the structure of the glass changed as received material once we'd wetted it and sort of ground it up before we've put it into the press, and once it had been sintered completely. And you can see that you get a dip in the higher sort of the Q3 silicon species, so you're getting a reduction in the overall network connectivity, which is what you would expect. And then when it's heated and resintered, you get a repolymerization in the silica. And we also see that you get phosphate ions pop out when you add the water, and then they sort of get resorbed back into the structure. So you end up with no Q0 phosphate ions in the final material. So that kind of helped us understand the mechanism that's going on. And then because we were working at just 100 degrees, it's a prime candidate for making composites with polymers. And we chose PLA, which is a really fairly readily available, quite cheap polymer. And we made a full sweep from 0 to 100% at, again, just 100 degrees. And you can see on the left two SEM images that we've got a structure of the PLA, which is quite dense with the sort of channels where bioglass would be able to sit and would be able to move through the structure if it needed to. And then on the right hand side, two images, we have about 60 volume percent bioglass. So you can see sort of two distinct regions begin to occur. You've got a structure of the PLA, and then in between that, you've got the bioglass. We've also got some really interesting features in that we think we've got hydroxyapatite beginning to form during cold sintering, which is a really good thing for us because it shows us that we're still really quite bioactive, because that's the main sort of the last step, if you like, in those first 5 that I talked about in the sort of the reaction with the body once we've implanted our sample. So the next thing that we looked at was actually, is this cytotoxic? Is making these components via cold sintering making it more cytotoxic than conventional samples? So we compared all the different bioglass polymer composites with TCP and just the PLA after a 7-day sort of dwell in media, which allowed for initial alkali ions to sort of dissolve into the solvent. And we did that so that as we were doing it in a closed system, so we didn't overwhelm the sort of the cells that we then used. But we can see that up until after 7 days, everything is above the red line. So we're above this red line on day 7, which implies that we aren't in this sort of cytotoxic range, which gives us really encouraging things that we could be in the body. We would probably find even better results from this, because you're sort of always constantly changing your media essentially. And some pictures of the cells that grew onto that, so the cells that created the metabolic activity. And you can see that on day 1, the 100% bioglass is having a significant effect, and that was shown in the graph as well. And then by day 7, everything up to 70 weight percent bioglass, which is about 60 volume percent, the cells have got so confluent that you actually can't see the individual cells anymore. So we've got some really exciting results that basically show that you can make these cold sintered polymers at 100 degrees, so and keep the sort of really nice bioactive properties in our material. Yeah.
Sorry. Yes. So to summarize this quickly, I've gone over the effects of powder size and the effect of cold sintering of zinc oxide. Then I've talked about how we can introduce a dopant, gallium, if you want to introduce upscaling for the material into industry, and then shown the actual applications of cold sintering, and where we can produce devices which will be useful in applications of zinc oxide in cold sintering. And then Jess has taken us over bioglass, which is very important in biology applications and medical applications, and how we can combine them with PLA composites and the really good cytotoxic results we're having with the cold sintered material. Acknowledgements. I'd like to thank Functional Materials and Devices, University of Sheffield, all of the staff that have helped us through our work. Johnson Matthey for providing all the support throughout these projects and the research. UCL for providing the initial gallium oxide powder that I used. And of course, the University of Warwick for doing the other research that's on Jess's work. Thank you very much. Any questions? Free to ask.
So thank you very much, guys. Well, I know the work, of course. So there's a question from Laura. Thanks for a really good presentation. You shared the need to control very precisely the composition, powder impurity levels of your stack. How does this affect resulting microstructures? And so you've got a question relating to how heavy clay sites in particular, you use clay from the local quarry near the manufacturer, which can differ from batch to batch quarried. So what opportunities might there be if using it in heavy clay, or is it in the too difficult category? Wow, okay, that's a tough question. Do you want me to take that, guys?
I don't know.
Yeah.
Give it a go.
Oh, well, I'm going to do the usual cop-out. We've never really tried. It is interesting. Remember the densification law, of course, you know this full well, when you have a viscous phase that forms because of reactions at high temperature. So we would circumnavigate that. We'd have to probably just relook at things to begin with, and take a different approach to getting to the same type of product, because we don't have the temperature to create the decomposition of the clay, which reacts with whatever you've added to it to create the viscous medium, which does the densification. So it's a different process. So we'd have to relook at how we make things, and that would make it extremely disruptive and not something which would iteratively add on to a heavy clay production route. But David, in his last talk, alluded to an ability to do alumina silica refractory composites. We can do that by cold sintering, and we can do it by the hybrid technique. And that is a large volume business. It's shaped bricks. It's not castables, of course. It's shaped bricks, which we require handling characteristics for. And we can get those handling characteristics, at least in the lab, in small pellets based on our cold sintering and hybrid sintering routes. So there is applications potentially for larger volume industries, in addition to these high value manufacturing industries, such as the bio stuff and anything to do with electronics, zinc oxide, barium titanate, and things like that. There's one question here. Paul has asked, engineering challenges for applying such high pressures to high volumes of ceramics glasses. Do you want to take this one, guys?
Yeah, I'll take it if you want. Yeah, so reducing that pressure is really, really important. Of course, in the presentation, I showed that things like 375 megapascals, the high densification of zinc oxide, we have managed to get below 200 megapascals. Some groups in published research have managed to get it lower. It is definitely something that needs to be reduced if you want to really upscale this process. But we reckon that reducing the thickness as well will possibly allow us to reduce the amount of pressure that we actually need, hopefully. If we've got very, very thin layers, perhaps we won't need the amount of pressure that we would for such thick layers. Do you have anything to add, Jess?
Yeah, I would just say, obviously, Paul's question is about the sort of high volume side of things. And if we're looking at sort of bigger components and larger amounts of material, obviously you do get into the region where you need bigger presses for higher pressures. But like Dan said, with work, you can achieve lower pressures, but you'd also have to be quite careful about any sort of differences between sort of inhomogeneity between sort of contact surfaces and then your bulk. And that's something that people have started to see, that if they've got two large samples, you might get different properties at different parts of the sample. So I think that's a definite challenge, and that we don't understand how to control that necessarily, other than reducing the thickness.
I think those are good answers. I would add that we do now have some materials that we can do at 50 megapascals in the lab, and they are materials that potentially have commercial applications. So it is a target thing, Paul, and it is an ongoing thing. And for sure, we're not for 600 megapascals or something like that. If you scaled it up to a 10 by 10 centimeter part, you're in trouble. So it has to be done. But we're moving in that direction, and it's a matter of what technology will work with this technology. I think that's the thing. I'm afraid, despite it being my pet topic, of course, I'd just like to thank Jess and Dan for giving a talk. They were very nervous and did a great job, so thank you very much. So, Bill, do you want to get going?
Yeah, no problem, Ian.
Thanks.
I'll just try and share my screen, which tends to be a rather interesting process. Right, can you see that?
All right, I didn't introduce you, Bill. So,
oh, feel free.
So yeah, sorry. So it's Bill Lee. He's now the Professor of Materials for Nuclear Energy and Extreme Environments at the University of Bangor. If you want to know who's responsible for bringing into the UK academic community, you can blame Bill. Okay, so if anybody is upset with me, blame him, not me. So over to you, Bill.
Can you see my slides, Ian?
Yeah. You just need to go to screen presentation mode.
Okay. Well, thanks, Ian. And can I just say how much I've enjoyed the talks today? There've been some fabulous talks, and I've learned a lot. And I was hoping to meet people in person. In fact, the only reason I accepted this invitation was so I could come up and meet people and go to the Red Deer and drink beer and chat. So sadly, we can't do that. So you just get me in a little box in the middle of your room. So anyway, what I plan to do in the next 15-20 minutes or so is just to gaze into my crystal ball. I have many years experience working with the ceramics sector and also with the refractory sector and the nuclear sector. And I'm sort of rather pleased that we've got the American Ceramic Society UK chapter involved and the Foundation Industries Network Plus, and because it sort of fits with a lot of things I've done in my career. So it's a great pleasure to have the opportunity to talk about some of these things. So as Ian said, I'm now at Bangor University. Over the last 4 years, we've been setting up a small nuclear engineering group there. So we now have 9 academics and 11 postdocs and 10 research students working with us in a whole raft of different areas, which are shown on the figure in the bottom left of this slide. So I've always liked gazing into my crystal ball. So a few years ago, I did that. In this little article for a guest editorial on the contribution of ceramics to environmental cleanup. And the basic problem is there's too many people on the planet, and coupled with increased industrialization of less developed nations, we're just generating a lot of pollutants, solid, liquid and gas, and many of the latter contribute to global warming. And this is still a problem. That bulletin is from the March issue from this year. So we're still looking for that sustainable energy future. I also wrote an article with a few co-authors shown here for the global roadmap for the ceramic and glass technology in the proceedings of the first ICC. And I just highlight, in the longer term, reduction in CO2 emissions associated with the manufacture of ceramic projects will be achieved by replacing high temperature sintered or melted products by chemically bound materials that form at room temperature. And it's the development of room temperature ceramic systems which don't produce CO2 in their manufacture, but which harden and set by reactions that use CO2 is crucial. And increasing research efforts will be made to use ceramics for both carbon sequestration and hydrogen storage. And I think those things have happened with greater or lesser success. Now, there is a big push in the planet for net zero by 2050. And the way I look at this is we have various options in the energy intensive industries. We could go for low temperature processing, such as cold sintering, and we've heard a lot about that already. From Jess and Daniel. We can focus energy down into small volumes, such as in additive layer manufacture or some of the additive layer manufacture techniques. We can use the rapid sintering techniques, such as spark plasma sintering and the flash sintering, which we heard about from David. And we can use some sort of combinations of some of those techniques. In addition, we can reduce CO2 generation by using technologies that don't generate CO2, so magnesia cements rather than lime-based, carbonate-based, aluminosilicate geopolymers, which are really glasses, and the sort of technology associated with direct reduction of steel using hydrogen. So I'm going to talk about some of these in a little detail, and some I'm just going to ignore completely because I don't have time. You'll be pleased to hear. Other opportunities, thermal management technologies using the same sort of model as Rolls-Royce used to control their jet engines worldwide. And then I'll just mention a little at the end on where I see things going, which is all of those things on this list. But I think there's a real need in the UK and worldwide for industrial parks. And I'm a nuclear engineer, so I'm going to push for nuclear reactors to be built to generate green hydrogen, jet fuel, and do other things. And I'll demonstrate, I hope, how we can do that. So I heard, I've worked with Clive Randall for many years. So Clive, Ian and I go back a long way. I think his cold sintering work is a game changer, and I'm pleased to see people picking it up. He gave a very nice talk fairly recently at the Foundation Industries Network Plus meeting, and since we've already heard about it, I won't give you any of the sort of technical detail. But what I think is a crucial aspect of that is this ability to co-sinter, where you can merge materials with very different behavior and properties and integrate them into a single system or unit. And I think that's the great power for cold sintering. So I think it has a role to play, that sort of technology. And I include sort of cement-based technology in that, magnesia cements, in this cold sintering, low temperature processing. And it will be important in functional ceramics, I don't doubt. We heard about zinc oxide and barium titanate already. More difficult for the high volume, low cost structural ceramics, like the sort of materials that Laura covers in her talk earlier on. I've sort of seen this figure earlier, but it just shows the energy needed to densify ceramics as a function of time. And you can see conventional sintering in the top right, and flash sintering, which we heard about in the bottom left, and the hot press, the hipping, SPS, and microwave sintering in between. In the top right-hand corner is a shameless plug for the book that I helped rewrite with Dave Richardson recently. And a lot of the figures I'm using here came from that work with Dave. So associated with some of those techniques is sort of rapid sintering techniques where you can use a range of fields applied. We heard about electric, but there are other options. SPS, which many of us have come across, where you're using this pulsed electric current plus rapid heating and uniaxial pressure simultaneously, and you can get to very high temperatures above 2000 degrees C in very quick times, in just a few seconds. And there's been a lot of work in the ultra high temperature ceramic sector on this, but you do need specialized equipment. It is a batch process, not really suitable for the high volume ceramics. That will be needed in order to decarbonize the energy intensive industries. So as well as sort of rapid use of energy, so you minimize the amount you use, as well as low temperature processing, you can focus the energy, and additive layer manufacture is a really important aspect, more important with polymers and metals, but becoming important in the ceramics sector. And the table just shows various additive layer manufacturing techniques. The figure is a diagram which my colleague Michael Ruston at Bangor drew for me for the textbook with Dave Richardson. An additive layer, it has a lot of advantages, can use computer-assisted design and manufacture. You don't have large setup costs, you can be flexible, produce a lot of complex shape components. But again, it doesn't really fit the foundation industries types of materials. I think merging some of these technologies, additive layer manufacture plus flash sintering, additive layer manufacturer plus cold sintering, and some of the things we heard about earlier today are important. And here's another recent bulletin issue. I think this one's April this year. And I think merging these things has a lot of potential in future, and maybe we could get to industrial scale, you know, high volume materials, but there's much research that's needed to do that. So the other area that I'd like to flag up is that of thermal management. So I'm sure many of you are familiar with how Rolls-Royce sell their jet engines. They don't sell the engine, say, here, take an engine, give us lots of money. That doesn't work like that. What the airlines do is buy time in the air, not the engines. And all Rolls-Royce engines are censored, so they have sensors all over them, and they're monitored from a single room in Derby, so that they know when repair and replacement is needed. I believe that in future, refractories companies will follow this sort of model, and ceramics companies eventually, where they sell time at temperature. They don't sell a refractory brick. They'll sell you a furnace that you get so many hours at the temperature you need. The sensors will be installed around the furnace in various types of furnaces, and the whole fleet will be monitored, and repairs and relines will be done from a single location. There's much that needs to be done in that sector in terms of developing sensors for the extreme environments, and the process monitoring and clusters of sensors, and then you get lots of data and you have to monitor in real time. And Laura mentioned this earlier. And I think that is the future for these sort of costly, high energy using, carbon generating industries. It may not be next year, it may not be 5 years, but I think it's going to come eventually. So what we are on a path to now is net zero by 2050, and governments all over the world are buying into the concept. I'm afraid I don't think that there's any chance of achieving net zero by 2050 without a significant expansion in our nuclear power generation capability, because we need all that electricity to drive those electric vehicles and charge up the batteries that we've heard about. We need to decarbonize transport, and we need heat production, and we need to generate hydrogen fuel for transport and heat, should we follow the hydrogen path, which it looks like we're going to. And some of these industries are just very difficult to decarbonize, and we've talked about those earlier today. So there's a significant increase in low carbon electricity production going to be needed. And if you do the sums, the numbers are enormous. And even to generate hydrogen, you know, we're going to need everything we can throw at this issue to get net 50 by 2050. We need all the renewables we can get. We need a nuclear power because it's a low carbon, it doesn't generate carbon. And then you need to work on the grid because you've got these intermittent sources of energy, and you have to balance that. And none of this is easy. And there's a massive need for governments, and I mean governments all over the world, to come up with a roadmap on how we can achieve this. They all come up with lovely words saying they will, but they don't say how they're going to do it. And frankly, it's not going to be easy, and we need to educate people on how it's going to impact their lives. And it's an exciting opportunity and a real opportunity for younger engineers out there to make a difference. So what's the UK nuclear situation? So the UK has generated historically about 20% of its electricity from nuclear since the late 50s. All the big reactors are going to close in the next 2 years, apart from one. That means we lose all that low carbon electricity generation. There's one new build underway at Hinkley Point, but we need more large reactors, and the 2 sites that are up for grabs at the moment are in Suffolk and North Wales. But we also need not just to replace the reactors that we're losing, we need a whole program of new build in order to achieve net zero by 2050. And the sort of reactors that are being looked at are small modular reactors, and there's a Rolls-Royce consortium, UK SMR consortium being put together, working with government on that, and advanced modular reactors, which might be fast breeders. What they bring is high temperature capability and the ability to co-generate. And that means they can do things like produce hydrogen, fuel, produce ammonia and jet fuel, as well as electricity. So, but if we're going to do that, these things have to start now. I'll not dwell on the types of reactors because I don't think it's important to this audience, but the small modular reactors are being built now. There's a big push in the UK. The government is committing £250 million to Rolls-Royce to support their programme. SMRs are good and will be important for the UK in generating electricity. But what they don't do is give you enough high temperature so that you can also generate green hydrogen and ammonia and similar. So at Bangor, a little group has been writing a report which we're pointing at in the way of important people in government on advanced modular reactors. And they will be important, and they will be important because they enable you to produce power when the renewables are not working. So when the sun's not shining and the wind's not blowing, you need something else. So this is termed dispatchable power that they fill in the gaps. They also offer flexibility because of this high temperature heat you can generate from them, which you don't get from small modular reactors. And they can push the UK's low carbon agenda, but we have to build them, we have to choose a design, we have to set up a program to do it, we need the funding and the regulatory system and the supply chain. And these things are all possible, but the government needs to move on it now. So that's the points on the lower bullets. This just illustrates the sort of temperature ranges and you get from various reactors on the bottom of the picture, and then the temperature ranges you need for the various desalination programs or district heating, and you can get that from waste heat from reactors, the sort of heat that gets in the seawater these days. You can see SMRs, but you only get about 300 degrees C from them, so that enables you to do a few things in the sort of petrochemical sector. But if you want to get to the foundation industries, then you need much higher temperatures, and then you need the advanced modular reactors that produce that sort of high temperature heat, as the people in the know call it. I was involved in a program report to a government briefing document through the Royal Society on cogeneration, and this just highlights the output of that. So cogeneration is that you use a nuclear reactor not just for electricity but to do other things. And on the low temperature, perhaps with small modular reactors, you can do district heating and seawater desalination. Well, we don't need seawater desalination in the UK. We got plenty of water. but we do need to decarbonize industry. We do need hydrogen, and you know, you can use that heat for direct air capture, and you can store the heat in molten salts, various other things. So what that leads me to, and this is the sort of most interesting slide, I think, is the concept of an industrial heat park, where you have an advanced reactor and it provides district heating, it provides the heat for steel production, chemical plant, hydrogen production, and cement production too. So if we can persuade government and that this concept of a park of industry, which frankly we already do, then I do believe this is the way forward, and I suspect other countries will pursue these sort of options as well. In fact, I know some of them are already. So just to conclude, so I think low temperature and energy focused ceramic processing technologies definitely going to be important, and we'll find a lot of applications in the composites and functional sectors, and some in the structural, and maybe in the long term more in the structural. I think the sort of thermal management technology that I highlighted, sort of similar to the Rolls-Royce jet engine model, will be applied. And I think that'll be a sort of global industrial thing. And then I envisage that these industrial heat parks constructed around nuclear reactors will be part of the future. And then a last bullet, and perhaps mildly controversially, and it aligns with Laura's map of the UK earlier to some extent. These are the heavy industry areas which would benefit from the construction of an advanced modular reactor located with them. Some, like Hartlepool, already have a decommissioned nuclear licensed site, decommissioned reactor where one could go, and they will probably be the first to go forward. So I'll stop there. And I'm sure I've run over, and I'm sure if there were questions on the chat, I haven't had a chance to see them, but I'm happy to answer any questions. And thank you.
Excuse me. Thanks very much, Bill. That was really good insight into what we might see in the future. Probably what we will see. Any questions for Bill? Justine Trino Mark has rejoined, and he will complete his talk after this, so we're not quite finished. So any questions for Bill on this? So you just don't believe that the other renewable resources are capable of generating the volumes of electricity you're going to need?
No, not a chance in hell. And actually, Laura's put a question on the economics. Yeah, I think, Laura, that government's going to have to reach into its pocket rather than rely on the Chinese and French governments to fund the reactors like they have at Hinkley Point. I think it's much more sensible that the UK taxpayer underpinned the construction, and I think it's going to happen with the Rolls-Royce UK SMR consortium, and I think because SMRs can't do the hard to decarbonize industries, that the AMR will have to be constructed almost simultaneous with the SMRs, and there are one or two technologies that are ready to go, and other countries are constructing them.
Do you think there's a political will to build more nuclear reactors?
I think there's a political realization that they're going to have to come clean with the public before too much longer. I don't know when it's going to be, Ian, but I'm afraid you do the sums, there's no way it works out.
I agree with you.
I
agree. It's an inevitability, but it's I don't know. People take a long time to do the inevitable, which seems bizarre. In terms of establishing new generation nuclear plants, are there particular need uses for certain functional ceramics such as CMCs?
Yeah, that's a very good question. Thank you, Tabs. The other aspect that I didn't touch on is fusion. I'm actually working with UK AEA, a little company called Tokamak Energy. And we've just set up a silicon carbide consortium, or it's just being set up, to look into use of silicon carbide in fusion, not just fission. So I know it's being looked at as a cladding material for accident-tolerant fuels in fission, but there are various options for using silicon carbide in fusion reactors. And of course, eventually we'll get to fusion, but it won't be until after we've built the next generation of fission reactors.
Okay, I'm in agreement. We need to do this. Build them as safe as we can, but we need to do it. I'm going to change tack now a little bit, and we're going to move on to a talk by Mark Fevieux. You know, all these years I've been working with you, and I still haven't known how to pronounce your last name properly. So my real apologies for that.
It's okay. It's okay. It's Fevieux, but I mean, you know, that was pretty close.
I probably said it wrong, and you've been too polite for God knows how many years. He's the principal research scientist at Johnson Matthey, and I've been working principally on various different conductivity materials, but specifically in the last year or two on all solid-state batteries. And he's going to give an overview of the state of the art in that area. So I'm going to hand over to Mark.
Yeah, thanks, Ian. Right. Let me just put this onto presentation. And I hope everyone can see my slides. Is that? Set the pointer. Here we go.
Right, yes. That's fine. I can see them.
Great, cheers. Okay, so this is my take on the state of the art for all solid state batteries, looking at the materials and challenges. It really is an enormous topic. So I'll do my best to introduce some of these challenges, but that's all I can do, I'm afraid. So decarbonisation of the transport sector will help us achieve net greenhouse gas emissions of 0 by 2050. One of the major ways to do that is to electrify vehicle drivetrains, and primarily, at least in the mid to near futures, that'll be through electric vehicles, battery electric vehicles, with fuel cell vehicles perhaps coming on along later. But some of the main factors currently affecting mass consumer uptake of electric vehicles, apart from the price, are charging times, safety, and range anxiety. Now, range anxiety is simply limited to the energy density of the batteries. And so to increase that, we have to look to some beyond lithium-ion technologies, one of which is all solid-state batteries. Now let's just compare a conventional cell in the top here with a solid-state alternative at the bottom. The conventional lithium-ion battery comprises of a porous graphite anode, separated from a porous metal oxide cathode by a porous organic polymer membrane. And this is all bathed in organic liquids, electrolytes that allow the passage of lithium ions from side to side as the electrons flow through an external circuit. Now, when you switch from that cell to an all solid state cell, we substitute the porous graphite anode for a lithium metal anode, and the porous polymer for a dense piece of ceramic usually, although it could be actually a dense piece of polymer or a mixture of the two. But I'll be concentrating on ceramics today. The cathode materials tend to be the same or similar. Now, energy density is described in one of two ways. First is volumetric, well, first is gravimetrically rather, which is watt-hours per kilo. And the second is volumetrically, which is watt-hours per litre. And this simple schematic clearly shows the volumetric energy density improvements that can be achieved. According to this data here, you've got 250 going up to 750 watt-hours per litre. Now, the gravimetric alternative is a bit more, there are a few more subtleties at play. It comes a lot down to the choice of materials and the way you process and deposit those materials. But I should point out that both of these are highly dependent on the successful inclusion of the lithium metal anode into the system, primarily because of its near tenfold increase in theoretical capacity compared to lithiated graphite. And once you combine a lithium metal anode with high voltage, high capacity cathodes, you can achieve some significant advances. Yeah, so back to materials choice. This data, this chart was taken from reference 2, and it shows how materials choice and chemistries clearly have a huge impact on gravimetric energy density. For example, take this sulfide material, it's lithium, germanium, phosphorus sulfide, thiophosphate even. If you combine that with this cathode material in red, in its thinnest form, a 30 micron layer, you can achieve energy densities in excess of 500 watt hours per kilo. In contrast, a much denser electrolyte, a lithium lanthanum zirconium oxide, a garnet type of material, if you combine that with some of these other cathode materials, perhaps in thicker layers of electrolytes, the energy density is nearly half that. So there's a lot riding on getting the materials choices right and processing them right to thin layers. On top of that, in the absence of the organic liquids, the things are much safer in terms of flammability and explosion risks. So why is Johnson Matthey interested in all solid state batteries? Well, we currently have a battery materials business, which is focused at the moment on cathode materials. You may have come across our enhanced lithium nickel oxide material in the press, perhaps. But also we undertake a whole range of R&D activities looking at next generation technologies, and all solid state batteries figure heavily on all of the battery technology roadmaps in the next 5 to 10 years. So in an all solid state cell, we have a cathode composite material, or a composite cathode even, which comprises your active material, your electrochemically active material, lithium cobalt oxide, for example, in close contact with your electrolyte ceramic material, and there'll be carbonaceous materials in here to impart electronic conductivity, whilst the electrolyte material takes care of ionic conductivity. And during charging, the lithium ions pass out of your active material through the electrolyte and are plated out at the lithium metal anode. And then during discharge, the lithium ions are stripped back from the metal anode, pass back through the electrolyte, and are recombined with your active material in the cathode. And this repeated electrochemical cycling is accompanied by a whole raft of physical and chemical processes that occur mainly at the interfaces in these cells. Commercialization is very much an interfacial challenge. Really, it is for solid state batteries. I'll mention anodes briefly. I won't go in any more detail into these, but interfaces at the anode are absolutely critical in to achieve successful integration of lithium metal into these systems. And it's all about mass transport management. You're managing the transport of lithium ions through the metal anode to the interface and away again through the electrolyte. If there's any mismatch in that transport process, you will end up with perhaps stripping out of lithium from your anode surface, leaving voids, increasing the current density beyond critical levels, and causing all sorts of problems, including dendrite formation. These are thin filaments of lithium which can grow and penetrate even the densest of ceramics over time, leading to short circuits and cell failure. The kind of automotive targets we have at the moment are 3 to 5 milliamps per square centimeter, which is well above most of the academic literature. I'll come on to cathodes in a little bit later. Other challenges exist in the world of electrolyte synthesis and discovery. There are loads of electrolytes. Some of them have conductivities in excess of liquid organics electrolytes. Broadly speaking, there's 5 or so families, which is self-explanatory. In terms of what I've called others, they're sort of borohydrides, hydrides, and carboranes. And within each of these families, there are loads of subfamilies as well. In terms of processing and fabrication, I won't be able to cover that too much today, or barely at all, in fact, but I would refer you to some of these really detailed reviews, because it's all about the technology required and the environments required to deposit and form small dispersions of small ceramic particles, and making thin layers and making them bond well to give us robust battery systems. Now, I said I wouldn't really talk about fabrication, and that's not changed, but this is a couple of schematics showing the different setups or systems for solid state batteries. But the thing I wanted to take home, the take home message from this slide really is the calculated solid state electrolyte layers required for a 500 watt hour per kilo energy density has been calculated in the densest case, the LLZO case, to be sub 5 microns, which is a considerable challenge, and I think it's one the ceramics community should take up with gusto. It increases the challenge becomes less so with less dense materials. So the sulfides can be thicker and polymers thicker still. But there are other problems with sulfides, as you might guess. Keep away from moisture and that kind of thing. So back to electrolytes. What do we need in a good electrolyte material, apart from the fact that it needs to be formed into a dense ceramic piece? We need superionic conductivity for a starter. This is roughly or loosely defined as conductivity above 10 to the minus 4 Siemens per centimeter at room temperature. And what sets a superionic conductor apart from a regular ionic conductor is its capacity to facilitate concerted ionic motion through its lattice rather than a series of individual hops. So if we look at these sketches of a non-superionic conductor, classically you have an ion in a low energy situation, and it hops to a vacancy nearby through a transition state over an activation barrier, as shown again here. But the lithium ion probability associated with that process is solely located around the lithium ion sites. In contrast, a superionic conductor has a much flatter energy landscape profile. Some work by Yifei Mo and co-workers in the States identified 4 primary properties of the crystal lattices that impart superionic conductivity, and they've listed them here. I won't go through them, but some of the most interesting ones were the presence of enlarged sites in the lattice that can accommodate Coulombic repulsion between nearest neighbor lithium ions and establish a sort of variation on the local location of the lithium ion in that site. But anyway, as a consequence, all these things come together to impart this superionic conductivity, which is really what we're after in a decent solid state electrolyte. So apart from conductivity, electrochemical and chemical stability is of primary importance. And the electrochemical stability of a solid state electrolyte is defined as the potential above which you get oxidation by the cathode material and the potential below which you get reduction by the anode material. And these green windows here can be extended in practice, because these are theoretical. These are extended in practice by overpotentials that may be associated with the actual oxidation reactions. And so on this chart on the right here, the green bars with the extended dotted lines correspond to the real electrochemical stability windows for a range of sulfides here, which are all quite narrow, and oxides, which are much wider stability windows, spread over a wide range of values of potential. And this is all just correlates with their chemical composition. Really, that's what it comes down to. So this is the main thing that holds back sulfides, which are very highly conductive, much more conductive than oxides, but their narrow windows are somewhat of a handicap. Anyway, so as a consequence, when these things are run outside of their windows of stability, or indeed just through just under inherent conditions, open circuit voltage contact with the lithium metal, you can make these interphases, and these tend to be these binary compounds that represent the final decomposition products of these electrolyte materials. And problems really occur when these interphase materials are either ionically resistive, which would result in the increase in resistance of the cell, or they're electronically conductive, which results in the fast decomposition of your electrolyte and cell failure. The formation of these materials actually can be observed in test data, because these reactions consume lithium. There's so-called parasitic reactions. So this is just typical test data. You've got a charge it up to a certain voltage corresponding to a capacity, and then you discharge it, and the capacity is you don't achieve the same capacity back out of the battery. Let's represent a loss in lithium, because that lithium has been reacted to make some of these interphase compounds. And if they're stable, you can form a self-pacifying layer, and this will stabilize. If that doesn't stabilize, because perhaps it's electronically conductive, then eventually it all breaks down. So I mentioned the importance of managing to integrate a lithium metal anode, and there are a number of performance improvement strategies to overcome the main problems, which are wettability, chemical instability, and dendrite formation. I mentioned the dendrites earlier on, the thin tendrils which can lead to short circuiting. If we improve the wettability of the ceramic towards metallic lithium, we can make a more homogeneous interface, and that's going to modulate the current density, which is really important, and reduce the formation of dendrites. Loads of potential ways of doing that. One of which I've just highlighted here, which is the atomic layer deposition of alumina onto this garnet material. And the TEM from the literature shows that in the absence of the coating, you get this delamination, which is going to lead to inhomogeneous contact and different current densities. And you can see that the photograph shows the effect. The wetting is very poor. In the presence of the coating, the interface is much better, much more homogeneous, and so the wetting is improved, and that's advantageous. In terms of tackling the issues of chemical instability, there are all sorts of protection layers that can be used. Often these are based on polymers, and sometimes they include lithium salts or inorganic particles to improve ionic conductivity. The great thing about polymers is that they are flexible, and so they can buffer against the lithium metal anode volume expansion, which may happen during electrochemical cycling. And they can also modulate the ion transport at the surface so that diffusion, so there's no mismatch in ion diffusion around the anode interface, which is really important. Now, some of these, there are other techniques as well. A lot of these protection strategies from reference 5 have been highlighted in this figure here, and I refer you to that reference for a thorough rundown on them. So I'm going to finish off with the cathode. I mentioned the cathode earlier on. Volume expansion and contraction during electrochemical cycling of your active material, in this case a nickel cobalt manganese oxide, is really important. Dealing with that. Now these can expand and contract by up to 8% depending on depth of discharge. If they're bathed in a liquid, it's not a problem. However, in an all solid state cell, in this case the electrolyte is this lithium thiophosphate, the contraction during delithiation results in delamination of the active material from the electrolyte, and once that's cut off, it's electrochemically isolated, and so you lose the capacity of that material. And that is reflected in this initial data here. There's a 70 or 30% reduction in coulombic efficiency on just one cycle. This is the blue data. It charges up, and then you discharge it here, the first discharge, and you only achieve 70% of your coulombic efficiency because of the delamination effects, and that can carry on and on until you've got significantly worse performance. Now, I personally think this is an area that hasn't achieved much attention in the open literature, and I would say the ceramics industry could really would be nice if they could focus on that, as well as the chemistry industry, chemical academics and whatnot. But we do know that smaller active material particles can have different stress properties, and so the effects are lessened with the right particle size. And of course, matching your thermo or your elastic properties of your electrolytes with your active materials would also be a benefit. And not all active materials show this volume expansion. I mean, NCM is a common one, and it's good in many ways, but things like disordered rock salts and perhaps some spinel materials behave differently, and so the problems are different and lessened. Of course, there are also chemical reactions that can occur between sulfides and oxides, spontaneously, just chalcogenide exchange reactions forming mixed chalcogenide phases at the interface with detrimental results to the electrochemistry, and leads to space charging as well effects. Now, I mean, if you substitute the sulfide shown here for an oxide, there's a different requirements for densification. Most usually high temperature. You're all very familiar with the requirements of high temperature densification of ceramics. And in this case, when you've got mixed metal oxides in conjunction with other mixed metal oxides, you can form solid state reactions, these lanthanum cobaltates and lanthanum manganates in this case. Lithium niobate coatings can be used to inhibit that. But really, it's down to advanced sintering, I believe. And we've mentioned, some of the work earlier, the field-assisted and related techniques and cold sintering. And Ian mentioned that we'd had some fruitful collaborations in the past, and it's something that's I think should be pursued. And I was really impressed by the Lucidian prototype image. Would love to get my hands on that, of the kits for the dual cold and assisted flash sintering kit. Yeah. Anyway, so just to summarize, so the challenges are many, basically facing commercialization of all solid state batteries, but there is a huge and engaged technical community that's looking at this. And we've addressed all sorts of things, from ionic conductivity to interfacial stability, the issue of dendrites, energy density, and everything has been looked at, and so much has been done. But not many, whilst they've been very effective, not many have resulted in systems with current densities in the region of 3 to 5 milliamp hours per centimeter squared, and energy densities in around 500 kilowatts per kilogram. So there are significant challenges ahead still. And of course, on top of that, it needs to be economically viable. Of course, it comes down to, there's no market. So it's a technology push versus market pull. And the economics are changing all the time, despite significant investment from automotive OEMs in the likes of QuantumScape, a small battery startup, which has caused huge waves in the solid state community with their press releases. That's another story. So that's all I had to say on that. So I'm happy to take any questions if anyone's still there.
There's a few people left, don't worry, there's plenty to ask. Thank you, Mark. That's a really good overview. It's a shame it was in two halves, but there were two very good halves with an excellent intermission. So it's like the old days at the cinema, if anybody remembers that.
Oh, yeah.
So Bill's asked a question of you. Mark, when we get to the size of the global fleet, do we have enough of these battery materials available? I guess it's the lithium, the lanthanum, and so on. Is the purpose of this question?
That's a good question, and I don't know the answer to that myself, but by the time it comes to global fleet, every vehicle on the planet, presumably that means that's going to take a long time, and presumably you've got other technologies coming along, fuel cells, for example, I mentioned hydrogen combustion engines, all sorts, and multivalent batteries. I meant there are other technologies out there beyond lithium-ion technologies. You've got multivalent batteries using magnesium and aluminium. These are less well technically advanced, but they offer significant benefits over conventional lithium-ion wet cells as well. So it's a good question, and I'm just sort of skirted it a bit, but there you go. That was my answer.
And I think there's going to be a whole bunch of sister recycling technologies developed for these materials.
Of course, yes, of course, yeah, of course. And we have JM have a 2-century-old recycling business, which can easily be repurposed towards lithium-ion battery materials. So we need, we can maintain that circular economy.
Yeah, I think it's important. Derek comments, also batteries may be hired rather than purchased to aid recycling. So yeah, I guess that's a model that is going to be economically important in the future. Mm-hmm. We're only at the beginning of this because we've had only really a handful of electric cars on the road to date, and mm-hmm. We haven't really got to the recycling part. But I'm sure this is going to be huge in the next 10 years. Any more questions for Mark? Okay, well, it just is beholden to me to thank all the speakers. I think they've been all really excellent. I've enjoyed every one. Very diverse, but I think you can see that there's a central theme here about sustainability in various ways, either making ceramics less energy expensive or making ceramics that can reduce environmental pollution and reduce carbon consumption. I think there's a unifying theme. I think it's the thing that we should do probably the most in ceramics from now on in most sectors is to really move this agenda forward on this multiple level of sustainability. I certainly am doing that. That's my main focus now on multiple levels. Talking with Laura about helping the the clay industries, and also working on high-tech solutions for sintering and the creation of novel sustainable devices is where my three prongs of attack are at the moment. And so, yeah, I think I'm extremely pleased with the turnout and the talk. So thank you everybody for contributing. It's been a really, really good afternoon. It is an absolute shame, as Bill said, we couldn't meet up, but we are hoping to do an event in the back end of the year. We've got some tentative dates booked with the same venue, and I'm very hopeful that that will go ahead. But who knows? It's a strange world at the moment. Some of the scary numbers of yesterday might prevent that also from happening, but we'll keep you informed as to the potential venues, and we'll be in touch about speakers to give a flavour of ceramics, sustainable ceramics to that one as well, I suspect, but perhaps in a slightly different way. Okay, so thank you very much, everybody, and have a good rest of the afternoon.